we could relate the amount of organic loading with that of the amount of BOD needed or required with that of the amount of DO. With respect to the relationship of this, we normally follow the method in determining the DO so as to have its function with respect to BOD. Now, let's take the relationship of this in order to derive a certain equation on how to compute for the BOD of a particular organic waste. Now, as we have defined a while ago, the BOD5 is actually taken on the 5th day. Why? Because the bacteria that you need in order to degrade the organic waste would be stabilized or are found to stabilize after 5 days. Although you can have what you call BOD1, that means the oxygen demand needed to degrade the organic waste on day 1, day 2, day 3, and so on and so forth. However, it has been established that the bacteria could be inoculated for 5 days to make the microorganism more stable. And that's the reason why it is called BOD5. So BOD5, again, also is defined as the biochemical oxygen demand taken at 20 degrees. Why? Because we normally utilize the temperature of the laboratory as the temperature when we measure the amount of BOD as well as the amount of DO of a particular wastewater. So again, let's go to the derivation of the relationship of BOD with that of the organic waste. We can make use of this graph in order to correlate the organic waste with that of the BOD. If you would take the first graph, that is, you plot the organic removal starting from LO at time equals 0. With respect to the time from 0 to T as the days, you can have this graphical representation of slowly decreasing the organic waste as time passes by. And you would take note the initial organic loading at any time T would be equal or asymptotically equal to 0. Normally, that's the case, right? Let's say if you have a dried leaf, then you throw it in a river. After some time, what would you think would happen to the leaf? Definitely the leaf will be gone. And that's not magic. That means the leaf has been totally degraded in the water. So, the LO now decreases as time passes by and asymptotically reaches 0. However, if you would graph the oxygen consumption, that would be the BOD exerted, in order to degrade this particular organic waste, that is, the BOD would be increasing as time passes by. However, since this is your LO, you would realize that the BOD would be asymptotically reaches the same amount of initial organic waste. For that matter, we would say that at time T, and normally it has been found to be between 10 to 20 days, but we usually make use of 20 days as the time wherein the BOD reaches its maximum amount. And based on the graph, your BOD 20 can be numerically equal to your organic loading. For this matter, we would say, or we can call this BOD 20 as BODU. And this stands for ultimate BOD. So what's ultimate BOD? It's the maximum amount of BOD needed, or the oxygen demand needed, in order to totally decompose a certain organic waste. Now, how do we come up with a derived equation? Let's take this example. Equating both expressions, you would have this equation. This equation can be separated to have this equation. And this is equal to dLT over LT is equal to negative kdT. You can integrate this, both sides, with LO as a lower limit and LT as the upper limit at any time 0 to time t. So, integrating both sides, you have ln LT over LO is equal to minus k multiplied by t. To simplify this, get the exponents of both sides, this would be LT over LO is equal to e to the minus kt. From this expression, you would say that the amount of organic waste at any time t is equal to the initial organic loading multiplied by e to the minus k multiplied by t. But definitely, you cannot measure at any time the organic loading simply because it's already degrading in the wastewater. But you can measure at any point within the stream the BOD. And therefore, we could relate this equation with the original graph that we have shown a while ago. So, from here, the time of, or at any time t, the BODT can be represented as the initial organic loading, which is LO, minus the initial organic loading at time t. Having this relationship and relating it to the expression that we have derived, we can say that this is equal to LO minus LO multiplied by E to the minus K multiplied by T. Factoring out LO, we have LO 1 minus E to the minus K T. This would now be the amount of oxygen needed to decompose the organic waste at any time t. Recall that we have defined BOD5 at 20 degrees because we have taken the BOD concentration at the laboratory temperature of 20 degrees. But normally, when we start discharging the water, the ambient temperature would not be equal to the laboratory temperature. And therefore, the K that we have computed here would now be equal to 20 degrees Celsius and therefore not applicable to whatever ambient temperature of the body of water we're going to discharge the wastewater. Therefore, there must be a correlation of the change in temperature with that of the value of the rate decay constant. And this can be represented by this equation. You have capital K sub T, wherein capital K would be the rate decay constant at a specific temperature other than 20 degrees. And this is equivalent to K20. This is the rate constant of your organic waste at 20 degrees Celsius multiplied by an empirical constant, theta, raised to T, that's the temperature, minus 20 degrees. How do we know the value of theta? Based from different studies, theta would be depending on the range of temperature. So, we have 4 to 20 degrees as theta equal to 1.135. Since this is an empirical constant, these may vary depending on the set of data. But for the purpose of computation, we will be utilizing this for our problem solving. However, you can get the values of theta from any environmental reference book. And then, if the temperature would be higher than 20, that would be 20 to 30 degrees or even higher because we have already the problem of global warming. Let's make use of the theta equal to 1.056. How do we solve this problem? We can solve this problem by simply using your basic stoichiometry. Given you have 300 ppm of the carbonaceous component, you have CH2O as the organic waste. We all know that if this oxidizes, we use oxygen, and then assuming that there is complete oxidation, you have the product CO2 plus H2O. The next step would be to balance the given equation. So you have C, then you have 2H, and then you have 2, 3, 2, 3. So we have already a balanced equation. You start with the given to compute for CBOD, 300 milligrams per liter of the organic waste. You convert this to mole or millimole by getting the molecular weight of CH2O. This would be equal to 16 to 12. So we have 30 milligrams per millimole. Utilizing this molecular weight, we have 30 milligrams per 1 millimole. And then since we already have a balanced equation, 1 millimole of the organic waste is equal to 1 millimole of oxygen. Therefore, 1 millimole of CH2O is equal to 1 millimole of oxygen. However, to compute for the oxygen demand, we know that 1 millimole of oxygen is equal to 32 milligrams. So we cancel, then cancel. So finally, we have the value milligrams per liter. The value is 320 milligrams per liter or ppm. How about the nitrogenous component? How do we compute? We all know that the given is NH3-N. This means in environmental studies class that the nitrogen content will be coming from ammonia. So again, this doesn't mean that we have a gravimetric component or analysis to be utilized here. This only means that the nitrogen will be coming from ammonia, because we all know that if organic waste is degraded in water, the first thing is it will be converted to ammonia. So if the ammonia is in water and it is oxidized, we would say that the products would be the H plus as well as the nitrate ion, because based from nitrogen cycle, the ammonia will be converted to nitrate, plus of course the water wherein they are dissolved. So again, the next step would be to balance the equation. So you have 1N coming from ammonia, then you have 3H, so that would be 1H from the ion, H plus, and then 2 from water, and then we can now compute for the oxygen demand needed in terms of millimoles. So that would be 3 plus 1, so you should have 2 here. After having the balanced equation, we can now proceed in computing the NBOD. Starting from the given 50 milligrams per liter of N coming from ammonia, we convert this to millimole of nitrogen because we only represent the nitrogen here. So that would be 14 milligrams of N for every, or NH3N for every millimole of NH3N. So cancelling this out and multiplying it by the balanced stoichiometric coefficients, we have the relationship of 1 millimole ammonia or nitrogen in ammonia to that of 2 millimoles of oxygen. Then, compute for the amount of oxygen by multiplying this by the molar mass of oxygen. So you have 32 milligrams per 1 millimole of O2. This would cancel out to give us the value. Let's compute. This is 228.5 milligrams per liter of oxygen. The final question would be the theoretical oxygen demand, which represent the combination of the CBOD and NBOD. Therefore, we simply just add the two. So you have 320 milligrams per liter plus 228.5 milligrams per liter. This would give you 548.5 milligrams per liter. This schematic diagram shows you the methods utilized in the laboratory to determine the BOD as well as the BOD rate constant. It all starts with the proper sampling procedure. So normally, the wastewater is taken in a 300 ml BOD bottle, which is normally an amber bottle, so as to avoid photolysis, or it should be free from light, because we would like to preserve and stabilize the microorganism. Now, the bottle must also be free from bubbles. That means during the sampling, the bottle has to be filled up to the brim and has to be stoppered as soon as possible. Now, it is also recommended that all chemicals in the preparation of the sample for titration had to be placed at the middle of the sampling bottle. And here, it shows you that there should also be a dilution of O2. That is, you have to compare it with that of the blank. So, a blank would be your correction factor so as to completely compute for the dissolved oxygen. Now, we make use of the graph and the equation that we have utilized and derived so as to compute for the BOD as well as the BOD rate constant. Here, take note that when you compare it with the blank and when you inoculate the sample, it has to be incubated in a dark room, maintained at 20 degrees for a certain number of days. Let us reiterate that the number of days would be normally 5 days. That's why we normally measure the rate constant after 5 days. The next chemical organic property is chemical oxygen demand. However, this property can be correlated to BOD. Number one, because the BOD could be a good representation of COD, since COD is defined as the amount of dissolved oxygen needed to chemically oxidize the organic materials in water. So, in simpler terms, it means that if you know already the BOD, that could give you an idea what would be its COD. Depending on the type of wastewater, normally the BOD is twice the amount of COD. Now, another reason why you can correlate one from another, that is BOD to COD, is that in industry or in the laboratory, we normally make use of COD because it will take you only 2 hours, because instead of using bacteria which need to be inoculated, you only use here a strong oxidizing agent. Particularly, we make use of potassium dichromate. So this potassium dichromate could now be utilized to compute for the oxygen demand needed to integrate or to disintegrate the organic materials. The next chemical organic property is TOC, or known as total organic carbon. This is the amount of organic carbon in mixture as determined by instrumental method. You can measure this by acidifying and aerating the sample to remove inorganic carbon. Now, how is it done in the laboratory? You oxidize the organic carbon to convert it to CO2, and then at this state, with the presence of catalysis and absorbing medium, we determine the concentration of CO2 using spectrophotometer. Then we compute for the carbon content using gravimetric analysis. Some of the chemical organic properties would also be including phenolic substances, oils, and grease. Now, you have learned from your analytical lab that you can measure this using FTIR, or you can also make use of your UV-Vis to determine the concentration of these pollutants.